So this is a new chapter called Wave Optics, which is the second chapter in the field of optics in the category of optics. And in the introduction part, we discuss a few things like the theories put forward by different scientists in the past. So we are going to throw some light uh, on the theories of Descartes, Newton, Huygens, Thomas Young, and other contributions made by scientists like Foucault, etc. We are going to discuss a few introductory part to light. First, let me write here the name of the chapter. Name of the chapter. Optics. Optics. Introduction. Now, uh, of course, the first question that man asked himself was, "What is light?" Okay, what is light? And there were many theories. Light, is it made up of particles? Is it not made up of particles? If it is not made up of particles, then what is it made up of? And why does light travel the way it travels? Is the speed of the light infinite? As a matter of fact, man did not know whether the speed of light is finite. We know today it is finite. The speed of light is 3 into 10 raised to 8 meter per second, uh, which was also a very artful task to find the speed of light. But nevertheless, yeah. So whether the speed of light was finite or infinite, that was also a question. Many thought that the light speed of light is infinite, which was wrong. And then light showed various phenomena like reflection, refraction, then something called polarization, which we will see what it is. Polarization. Then we have something called interference, diffraction, scattering. Scattering of light, something you must have heard in lower grades. What is an example of scattering of light? The blue color of the sky is an example of scattering of light. On Earth, the sky is blue. There is no reason for the sky to be blue necessarily unless you have such an atmosphere. For example, on Mars, the color of the sky is butterscotch. CSOTCH. Is that correct? Butterscotch. The color of the sky is butterscotch. The color of the sky on moon is just black. There is no sky. I mean, roughly speaking, because there is no atmosphere, so there is nothing to scatter. Okay, so light scatters on Earth, and the atmosphere shows you blue light. So that was another of a property of light. Then you have dispersion. For example, dispersion. The example of dispersion is rainbow. A rainbow is an example of dispersion. Then, uh, of course, rainbow created by the droplets and the prism. So what you see in prism, light goes in and different colors come out. That is also dispersion of light. Okay, so uh, there are many properties of or characteristics of light that are unanswered. So different theories were put forward by different scientists. So in the introductory part, I will just say a few things on what the scientists did. Descartes, in the year 1637, this guy is the same guy after whom we name the Cartesian coordinate. Where can I write? Pencil. So you must have heard the word Cartesian. Cartesian coordinates. This word Cartesian, Cartes, comes from Descartes. Descartes. So he has done. He was a great scientist. He has done a good contribution in mathematics, of course, as you can see, and not to mention in physics, as his name is appearing over here. So he said light is made up of corpuscles. Corpuscles. What are corpuscles? It is just a fancy word for particles. Particles. Okay? It is just a fancy word for particles. So light is made up of corpuscles. In other words, light is made up of particles, is what Descartes said. And then there was Snell, who is famous, as you know, for what? Snell's law. Snell's law, which is related to refraction. Is that okay? And then you have Isaac Newton. In Isaac Newton also had the same belief that light is made up of corpuscles, and he wrote a few things like different color of light corresponds to different size of particles. For example, red may be a light made up of small particles, for example, and blue can be light made up of large particles. So different color of light is due to different size of particles, and reflection of light is because these particles bounce off exactly the way a tennis ball would bounce off, or anything else. Is that okay? So these particles bounce off, therefore you have reflection. This is what Newton said. So Newton was wrong, and that was also he said like the speed of light in water is more compared to the speed of light in vacuum. This is what Newton said. So he was wrong in this sense as well. So yeah. So this is an example. I mean, even great scientists can be right at one place and can be wrong at some other place. And Newton's theory was then corrected by Christian Huygens. This guy, Christian Huygens. They were roughly contemporaries. That is to say, they existed at the same time. Is that okay? It was around 1600s. Is that okay? So yeah. So Christian Huygens was another scientist who said that light is a wave. Okay, it is made up of waves. So he set forward a theory called wave theory of light, and he declined to accept that light is made up of particles. He said light is not made up of particles. He said light is made up of wave. Okay, I mean, and these waves are not particles, is what he meant. And he put forward a few assertions which were in contradiction with the corpuscular model of light, and details of which we are going to see in this chapter. Then there was Foucault, who did some experiments. Then there was Thomas Young, who did some experiments. Thomas Young performed uh, the milestone experiment, a classic experiment of interference pattern. So he interference interference of light. He discovered interference of light. Again, details of which we are going to see. And this experiment, Thomas Young's experiment, uh, established the fact that light is a wave, because interference property is shown only by wave. So if light is showing interference, it must be a wave. So the Young's experiment established the fact that the light is a wave. Okay. Then came along Maxwell. Maxwell unified the four laws of electromagnetism, which we have also seen in the last chapter of Physics 1. He unified all the four laws of electromagnetism, and mathematically, he was a great mathematician. So he mathematically derived a wave equation. A wave equation. He derived a wave equation, and that wave equation uh, predicted, I mean, that wave equation gave us an indication of what the speed of the wave would be. I mean, every wave equation does that. So every wave equation gives you an indication, at least theoretically, what the speed of the wave would be. Is that okay? And the speed of the wave, when it was compared with the values, practical values, turned out to be the speed of light. Speed of light. Is that okay? So it cannot be. I mean, it can be a coincidence, but on the other hand, it cannot be a coincidence as well. I mean, so Maxwell said that this wave has a certain speed, and this speed is exactly equal to the speed of light, and this can no be a coincidence, and therefore light is an electromagnetic wave. Light is what? It is an electromagnetic wave. So the question, I mean, this is all about asking what is light. So one is saying light is this, another is saying light is that, and Maxwell says light is an electromagnetic wave. Okay, so this is the most modern version of what is light. Is that okay? So see how theories evolve. It started off in the year around 1600s. Uh, then towards the time of Maxwell, I guess 1800s or so, the theories change. Perhaps in the future, our understanding of what light is will be further refined. Okay, will be further refined, and we will have a better understanding to what light is. Who knows? So this is what we have as an introduction. This part in blue or turquoise is what we will learn in this chapter. In this chapter, we will first discuss the original formulation of Huygens principle. We are going to discuss that, derive the laws of reflection and refraction. This is going to be interesting. Okay, laws of reflection and refraction is derived from a principle. Okay, from a principle. So this is going to be interesting. And then we will discuss the phenomena of interference based on superposition principle. And this is going to be important. Superposition principle is important wherever there are waves. Okay, it is a wave phenomena. It is a wave phenomena. Then towards the end, we are going to discuss polarization and diffraction and the transverse nature of electromagnetic waves. So these are the few things that we are going to discuss. So let us begin. So this was all about the introduction. The first thing that we are going to begin now is Huygens principle. Okay, so Huygens was a scientist. It is the name of the scientist, and he put forward a principle. To understand what his principle is, we will first have to understand a few things. Like he talks in the vocabulary of wavefront, wave normal, etc. Plane wave. So we have to understand what he means by these words. Okay, so we will have to discuss these terminologies. So Huygens principle. So Huygens principle, first I said we will have to understand a few things. Wave front. So first thing that we understand is something called a wave front. Now I want you all to imagine a calm water. Okay, this is an upper view of calm water. Now you drop a pebble at this place. What will happen? Waves will emerge from this place. Waves will emerge, and the waves will look like this, circular. These are crests. Okay, the waves will emerge and uh, they will flow in all possible directions. Okay, now you must have observed that waves go in circles. These waves go in circles, of course, and a certain circle is a locus. I hope you all know the meaning of the word locus. Locus of points, of all points which are in same phase, which are in same phase. Same phase in the sense they are vibrating in the same manner. So one is going up, everyone is going up. One is going down, then everyone is going down. Is that okay? So everyone's phase is the same, and these all are, second thing, coherent. Coherent. What is the meaning of coherent? Coherent means they have same phase and they have the same beginning in time. So same phase, basically same phase is technically called coherent. So coherent waves means all waves that have the same phase. Is that okay? So a wavefront is a locus of all points which are vibrating in the same phase and which will vibrate in the same phase as long as they exist. Okay, so this is what we have as wavefront. In the textbook it says wavefront is defined as a surface of constant phase. Okay, this is exactly what I said. Surface of constant phase. And Huygens said that wavefronts travel only in forward direction, and each wavefront acts as a secondary source of light. Okay, it acts as a secondary source of light. So every point, let me take this diagram on the paint, or I can do here as well. I mean every point, for example this point and this point on the same wavefront acts as a secondary source of light. So these all act as a secondary source of light and they move only in forward direction. So जैसे for example this point acted as a source of light and everything emerged from this. This point is same as this point over here. So this point is a source, this point is also a source. This point is a primary source and this point is a secondary source. So what is Huygens saying? Huygens is saying that every point on the wavefront acts as a secondary source of light emanating waves in forward direction just the way primary source did. Okay, so that is the thing. And energy of the wave travels in the direction perpendicular to the wave front. Now wave front means what? Wave front is basically a single wave. uh, uh, I mean wave front, it is exactly what we just discussed. I'm sorry, wave normal. I was trying to talk about wave normal. Now wave normal is this. I mean you have to draw a normal. So this arrow is wave normal. The word normal comes from the fact that it is going to be perpendicular to every point on the wave front. Okay. Then there are different kinds of wave fronts. You have a spherical wave front. You have a plane wave front. Okay. Plane wave front looks something like this. So all the points on this plane, single plane, are vibrating at the same phase. All the points on this plane are vibrating in the same phase. But the phase of this plane and this plane may be different. Is that okay? It is not necessary they will be same. So that is the thing. Uh, an example of plane wavefront is the wavefront that we receive for example sun. If you consider the sun, it emanates spherical wavefront. Okay, the sun emanates spherical wavefront. But if you are very tiny and you are very far away, then this section over here reaches us like a plane wavefront. Okay, So this small section is like a plane wavefront, apparently plane wavefront. Otherwise, it is a spherical wavefront. All right. Now, as I said, to understand Huygens principle, we will have to first understand the vocabulary. Now we are done with the vocabulary and we can talk about what the principle says. The principle says this material over here. Okay. Each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. These wavelets emanating from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at the later time. Now this is something interesting. Common tangent, I mean, this initial part is something I have already told. Every point on the wavefront acts as a secondary disturbance, and they act exactly the way primary source behave. Okay, so that is how light keeps moving forward, and yeah, we have something called a common tangent. Common tangent means, I guess I will draw a diagram over here. Common tangent means, suppose this is a certain wavefront, this is a single wavefront, okay, and as I said, according to Huygens principle, all these points, for example, I have drawn 4, I can draw many of them. All these points emanate secondary waves. Okay, so in 1 second, this point will emanate this wavefront in 1 second. In 1 second, this one will emanate exactly the similar wavefront, because one speed of light is the same. Speed of light is the same, and hence all these small hemispheres I am drawing are equal in radius, because in 1 second all these points do the same thing. Okay, now if I draw a tangent like this over here, and a tangent like this over here, and a tangent like this over here, and a tangent like this over here, then we can have many tangents like this. And if I draw infinitely many points like this, then we can have a common tangent. Common common tangent. Okay, we can have a common tangent, and that common tangent will look something like this. And this common tangent is the new wavefront, secondary wavefront. Is that okay? So wavefronts upon wavefronts are created by light. So common tangent to all spherical, we obtain the new position of the wavefront at the later time. So this is the new position. So a wavefront has now become this wavefront as time has elapsed. How much time? 1 second. I talked about 1 second. So this wavefront becomes this wavefront, and so on. It moves, keeps moving forward. So this is Huygens principle. Over here. Okay. Now, in the next video, we are going to talk about how exactly this principle explains reflection and refraction, because that is exactly what a theory is for. What is a theory for? A theory should explain something, that we observe. Otherwise it is just a set of words. So this theory explains something, and how it explains reflection and how it explains refraction is something that we will see in the next video. Thank you for your attention and watching the video.